Hello, everybody. Welcome to today's current seminar. Today we have two speakers. Our first speaker is Dr. Matthias Möller. He will be giving a talk on bridging the gap between isogeometric analysis and deep operator learning. Matthias Möller is an associate professor of numerical analysis at Delft University of Technology, the Netherlands. He earned his PhD in mathematics from TU Dartmouth University in 2008, and he joined TU Delft in 2013. His research focuses on developing numerical methods for computational PDE analysis. PDE research focuses on developing numerical methods for computational PDE analysis and the optimization of geometric designs. Currently, he is interested in combining classical numerical methods with concepts from scientific machine learning. Additionally, Matthias is exploring the implementation of these methods on high-performance computing systems and investigating algorithms to harness the potential of future quantum computers in numerical analysis and optimization. With that short introduction, the floor is yours and you can start your presentation.
Thanks very much, Nas, and thank you very much for being able to speak here in the Crunch seminar about actually a topic that is very close to my heart, so isogeometric analysis and scientific machine learning or deep operator learning. And as you see, there are a couple of people who I have to acknowledge who contributed to this work. So some of them are my former and current students and collaborators at TU Vienna, RWTH Aachen in Germany, and somewhere else. So before I dive into the topic, let me first zoom out and look at, let's say, why we do all this. Of course, as Nes already said, I'm interested in numerical methods, but also in the bigger picture in why or for do we use these numerical methods. And the keyword here is design through analysis. So what I mean by that is the following, that we are not just doing simulations per se or for their own sake, but we do simulations. So I use simulations at the moment as an analogy for analysis. We do this analysis to improve or optimize a design. So a design can be something from the car industry, a piece of a car or a car body. It could be a wing, it could be anything. A design can be just the shape, it could be the shape and the topology, but we can also think about different materials, or more modernly thinking metamaterials, yeah? And all of this comes together to a design, yeah, which we want to optimize, and not just visually that it looks nice, that it's a functional design, yeah? It should somehow resist stresses or resist loads, be aerodynamic, yeah? So it has to satisfy, or it has to obey to some physics laws, and that is what the analysis is responsible for. And to illustrate that, I have put some quote from a paper, and I'm not reading the entire quote, but just the highlighted one. So the potential value of design through analysis was demonstrated by a significant reduction in structure weight of the project vehicle. So this is obviously from the automotive industry. And this is not so surprising, but what is surprising is that this paper dates back to 1977. So at that time, there was not a big, or there weren't big computers that could do simulations in 3D as we do them today. But yeah, so here on the right, you see kind of the grid, the cut model or the analysis model that was used at that time. But what is exciting, that already at that time, the authors thought about using simulations to design something. And they even mentioned a lot of modern concepts, which we could even say can be in the paper from 2024. Yeah, they speak about computer-aided design. They speak about simulation-based analysis. At that time, it was something pre-finite elements or very low-order finite elements. And they even talk about interactive graphics, they call it, so interactive visualization. And the point they make is that they are not introducing these concepts as new methods. No, all these methods in a very rudimentary form have been around at that time, but they say the manner in which these techniques were integrated and applied in a design environment, that's the primary topic of that paper from 77. So, and now many years later, where the compute power is there to do really large simulations in 2D, in 3D with very good resolution. So this design through analysis concept, I want to pick it up and explain to you what our vision is, because what we want is a framework that allows both the rapid prototyping. So I use that for the, let's say, design exploration or pre-prototyping phase or prototyping phase. And then for the thorough analysis, with that, I mean, really number crunching to get very accurate results. And the important thing here is the word unified. So I don't want a finite element analysis for the second and something completely different for the prototyping. I want something that kind of seamlessly blends from the one to the other and seamlessly in mathematical sense. I want something that has the same mathematical background or framework. And the ingredients for that we use, and we'll go through most of them in this talk, is volumetric CAT. I say a few words what I mean by volumetric CAT. Then parametrization techniques, reparametrization techniques, isogeometric analysis, IGA. That's our, let's say, workhorse for the accurate simulation. And physics-informed machine learning, that's the thing that we see for the rapid prototyping. Volumetric CAT, what do I mean by that? Normally, CAT is just a surface description of your geometry. So you see it here. This tool would be composed of many surface patches, but you don't have anything inside. But for the real analysis, you also need, let's say, a mesh, if you so want, if you're coming from finite elements, or let's say control points in the interior. So we are really looking at trivariate parametrizations. Reparametrization, I don't have too much time to cover that, but I just want to mention it. Just looking from the outside, looking at the boundary of this G is equally good left and right. It's exactly representing it's a 2D parametrization, just to illustrate it. It is representing the same G. But of course, here on the left one, where you have not crossing, but very poorly aligned grid lines, very bad quality of the grid lines. If you would want to do an analysis on that, the outcome will be very poor. You will have, let's say, relatively high discretization errors. And the same, let's say, looking again from the outside, the same geometry, but with a much better interior parametrization. That is what I mean by reparametrization techniques that automatically convert something that you would design in your cut, that gives you automatically these nice and, let's say, analysis suitable, as you call it, parametrizations. Well, on that, we do for the accurate simulation IGA. You can also see it as a B-spline-based finite element analysis. These are the things we use from IGA, not more than that. And for the physics-informed machine learning, I hope I can show you how we kind of smoothly blend classical IGA to a deep operator learning framework. So the outline is logically as follows. So a few words about the mathematical core, B-splines, and IGA, and then how we develop from classical IGA these IGA nets. These are the physics-informed machine learning, or this is the physics-informed machine learning approach that I'm going to present here. And if time allows, I will also speak about some implementation details. Because it's all about speed, and if you are do some tricks here, you can really speed it up. And then finally want to give you some outlook on a new tool, a software tool that we are currently developing that allows these design through analysis with multiple people at the same time. So let's start with splines. And before we look into the math of it, I just want to show you that they really exist or existed in the real world. So you had some strips, wooden or plastic or metal strips. And if you fix them at some places, here, for example, you fix them here and there, and then here and here, they attain a shape. They attain the shape of minimum strain energy, yeah? And it is a smooth curve that you get. And then if you draw this curve, you can use it. It has been used in ship hull design and then was later adopted in the aircraft industry. But this idea of you have something which you fix at discrete points, at a few discrete points, and then you get a very smooth shape. That's also what we do in the mathematical counterpart of this. So now we come to the spline curves. And let me go through these three layers. So we first have the parametric domain. This is kind of, you are saying where you define basis functions. You can see it. In finite elements, you could see it as this is one element, this is another element, this is another element. But what we will see here is that these elements are a little bit wider. Yeah. Then in the intermediate layer, we see the basis functions, also very much like in finite elements. We define some basis functions. They look not really similar to the head functions finite elements, but they share some properties. For example, like the local support of basis functions, etc. And then at this third layer here, that's the physical domain. These are kind of the control points with which we define how the curve is the blue thing here, how it should look like. Yeah, and if we move these red points, we change the shape of the curve. Now, from this illustration, let's look a little bit into the math. Yeah, I have more or less the same splines here. And this is the lowest level. This is the parametric domain, the knot vector. Yeah, so you see it goes from 0 to 4, and some of them are repeated. We'll go into that in a moment. And then you are defining the basis functions recursively by per knot span, first having a piecewise constant one. You could see this as a lowest order basis function, something like a indicator function, and then you recursively build up higher order or higher degree B-splines from this de Boer formula. And well, let me illustrate what happens. For example, if we just have a single knot here, we have very smooth functions, yeah, to be exact. If we have a second degree spline, so quadratic spline, then the continuity here is C2 minus 1, so C1. Yeah, we have a higher than in classical finite elements, which are C0. We have a C1 basis function, overall C1. Now, what happens if we repeat knots in the interior? For example, here the 3, this knot 3 is repeated once, then the continuity, well, drops, it goes to C0. And this is somehow comparable to the finite element, the classical finite element case, where we just have a C0 continuity between elements. And yeah, at the boundary, we have no continuity. That means these points here can be really controlled fully by the control points. I repeatedly make this link to finite elements because they do share a lot of nice properties. For example, they have local support, a little bit broader than in classical finite elements, but still local. As you see, if you, for example, follow here this blue one, it goes over 2 knot spans and then is 0 elsewhere. What they do have, and that's not common in all finite elements, they are not negative. Yeah, they are either positive or 0. In finite elements, especially in higher order finite elements, you often have that the basis function has some part where it gets negative. That's a very nice property. And they share the partition of unity property, meaning that at any point in your domain, summing over all the basis functions, you recover the 1. Going from 1D or univariate to multivariate ones, there are many ways, also adaptive ways. Here we keep it as simple as possible. We just construct a tensor product basis. So we take the univariate basis functions in the one and the other direction and then put them into the tensor product. This slide is actually mostly for introducing notation, because now, from now on, boldface indices are multi-indices. Yeah, and these are the multi or the multiple parametric domains. And with that, we define the spline space very much like in standard finite elements. We have this basis expansion over all the basis functions, and the CIs here are the control points, or are the degrees of freedom with which we can control the geometry, but also the solution. Let me illustrate what I mean by that. And first we look at the geometry. So assume we have some basis functions here, and we want to represent this geometry, so this quarter annulus. How we do it is we define a so-called push-forward operator. That means these xi's are the control points here, the red ones, yeah, and then by moving around these control points in the physical domain, we get a push forward from the, this is a 0 to 4 squared domain. We push it forward into the physical domain. Like in finite elements, we can also go back with the so-called pullback. The difference is that in finite elements, the pullback is typically defined per element. Here it is defined on the full geometry, or to be more precise, on the full patch. Because if you have more complicated geometries, you typically use multiple of these and then have a multi-patch geometry. But let's skip this detail for the moment. Let's just focus on a single patch. So something which is, say, bijective to a unit square or to a square. So as I said, it's not, sorry, it's not only the geometry that is represented in terms of this basis, but everything else. For example, and we see it here, the boundary conditions. Yeah, here I have Dirichlet boundary conditions can be represented in terms of the basis, of course, restricted then to the boundary, and the control points or solution values at the boundary. And likewise, we can also represent load vectors or right-hand side in exactly this way. Yeah, and with these three ingredients, we can compute the solution, kind of the solution with fixed Dirichlet values, and what we actually compute are just the solution values in the interior, either with Galerkin isogeometric analysis, that's what most people do in the IGA community, or with collocation IGA, and that's actually what we do here, because that very elegantly blends to machine learning. So allow me to skip Galerkin IGA and immediately move on to collocation IGA. How is it derived? So if we look at the model problem, very simple, just linear. We have a linear differential operator acting on U in the interior, and we have another differential operator on the boundary. Yeah, it can be the identity if we have Dirichlet values, can be the normal derivative if we have Neumann values. And we derived a special weighted residual form. We're just weighting these residuals with some test functions and then integrating over the entire domain and over the boundary, and requiring that this weighted residual is 0. So what about these phi's? Well, these phi's, we are composing them from Dirac delta functions centered around some discrete points. So a couple of discrete points come from the interior, and another couple of discrete points come from the boundary. The important thing is that the sum of all these points equals n, and n is the number of basis functions. Actually, that means we need as many sampling points as we have basis functions. So with this expansion, or with this ansatz, if we are substituting this phi omega and this phi gamma here and here, then we are getting this requirement, which is really equivalent to that. So if we now look at what these coefficients Ci are, well, they are arbitrary. So basically, we don't need this here, but we can replace it by a a linear system of equations. So we drop the CIs and say for each CI that we had, we get an equation. So we get k equations for the interior residual, and we get n minus k, so the remaining the remaining number of equations for the boundary residual. And if we then substitute u by its basis expansion, so now here b are again the basis functions, u, j are the coefficients that we are after. If we are substituting them here, we get a linear system of equations that, if we solve it, gives us the unknowns u1 up to un. So I should say that this system is, of course, not dense. It is very sparse, like in finite elements. But just to give you an idea what is in the system, so I kept it dense for the moment. So a few remarks here. First is, since we are not what we would typically do in Galerkin, we are doing integration by parts. So we are shifting some derivatives from the trial to the test function. We're not doing that here. That means we have a higher requirement on the continuity. In particular, if this L is, for example, the Laplacian, so if we have second derivatives, then we also need C2 continuous basis functions. So that's why, or that's where B-splines, the higher continuity of B-splines is very helpful. And well, the same also for the boundary integrals, for the boundary differential operators, if we have, let's say, Neumann conditions, then we also need a higher continuity here. And the second thing I want to remark is, in order to solve this system, we have n unknowns, we need exactly n collocation points. So the number of collocation points needs to be equal to the number of basis functions. And we need that all these equations are linearly independent. So there shouldn't be any two collocation points that are the same. One thing, and I quickly go over that. So if you remember where we defined the basis functions, we defined them on the parameter domain, so on the Xi or 0, 1 domain. And of course, the physics is typically defined in terms of physical derivatives, so gradients with respect to x, y, and z. So whenever you see something like Lx bi of x, I just use this as a placeholder in the notation. We have to work it out to derivatives in terms of the parametric coordinates, and that involves a lot of, let's say, gradients, Hessians, determinants. We have a similar thing in finite elements when we do integration, integration on the reference element. But just keep this in mind, that whenever you see an L and B evaluated at X, there is some tedious work to be done to really implement it. So as I said, most people use Galerkin IGA. We do, or some people do collocation IGA. What's the difference? Well, the difference is that you have a larger error, but you also get something, and what you get is computational speed. So let's look at a very simple Poisson problem. Here, the solution is known, it's exact. It's all Dirichlet boundary conditions. And if we look at the error from the Galerkin IGA, it is very, very small. We can't even, nearly can't see it. Whereas with the same number of basis functions, we get quite some visible error if we use collocation IGA. And here, by the way, the collocation points are the ones you see here, the Greville abscissa. Of course, we can refine. We can refine the parameterization / the grid, and then see how does the error converge. But what we see here in the in the top right figure are the convergence rates if we increase the number of degrees of freedom for with dashed lines, Galerkin IGA versus collocation. And what we observe here, Galerkin IGA has optimal convergence rates order +1, h to the order +1, whereas in collocation, we see a suboptimal one. So one would have to compare this blue solid line with that blue dashed line that is both cubic. And we can only start at cubic because for Poisson we need C2 continuity, and cubic B-splines without any repeated knots is the first that gives us this C2 continuity. And another thing we see that there is some odd convergence behavior, namely that even say P is 4 and P is 5 give more or less the same convergence rates. So it's wise to not use the even ones because they really don't. The odd ones, because they really don't give us more than if you would use the even ones. What we do gain is, as I said, computational speed. So this is the computational time we need. And in Galerkin IGA, you have the problem of assembling the matrices with Gaussian quadrature or with some type of numerical quadrature. And that very quickly grows your computational time. You see it here, whereas collocation IGA is much quicker and doesn't grow so fast. So one might wonder, are the Greville points are the only points where we can collocate? And the answer is no. So we only have to obey the fact we need n collocation points, but where we place them, that's a little bit our choice. And there are other ways to place the collocation points, for example, these clustered superconverging points. So you see they have a slightly different structure on the parametric domain. And this, where you place the collocation points, also has an influence on the error. So you see here in the picture that the error looks different than in the than with Greville points. And if we do again the convergence study, we see that now dashed is collocation and bold is is Greville collocation, and bold is superconvergent points. You see that they improve the convergence rates. But one might ask if it is difficult to find the optimal position of the points, couldn't we just add more points? So instead of trying to optimize where we put these endpoints, couldn't we add more than endpoints and then reduce the error? And indeed, that's possible. And it's not an ad hoc approach that one can just do, but it is backed up theoretically. I come back to this expression in just a moment. So it's backed up by a paper from Lin et al., where they do exactly this and then derive some conditions under which this least squares collocation IGA is consistent and convergent. And basically these conditions say in each element there has to be at least 1 point, or you can add more. So let me go back. These are the elements. That basically means in each element there needs to be at least 1 point. And if we're adding more, we make it better. So let me get back to this expression here. What we do now is we still have n degrees of freedom / n basis functions, but we have more than that collocation points. So the matrix is no longer square. We can't solve it in the regular way, but we can solve it in the least squares sense. And let me say at this point already, this is why we chose for it. And this is how we kind of blend least squares collocation IGA into a machine learning or a physics-informed machine learning approach. Because this very much looks like a loss function that we can use in a neural network. So going back, does least squares collocation pay off compared to classical, say, with a square matrix collocation? Yeah, a little. Or we could otherwise say it does not deteriorate things. So now we see with IGAC, that is the classical collocation methods, dashed lines, And the bold lines here are the least squares collocation ones. We are either slightly better with more collocation points, or as good, yeah, for the orange ones, as good as the classical collocation. Yeah, and in terms of computational speed, well, we add more points, so it might slow down a little bit, but not significantly. But as I said already, for us, collocation, least squares collocation, IGA, is not the primary goal to just look at that, but least squares collocation, IGA, is a very natural framework, mathematical framework for us to blend it into some machine learning framework. Yeah? So this is again the formulation of least squares collocation, IGA. And allow me to bring this now step by step into something which we can then, on the next slides, use as inputs and outputs of a classical feed-forward neural network. So the first thing that we have done here is we replaced the differential operators with respect to x by differential operators with respect to the parametric coordinates, and we replaced the expansion, the UH, the unknown, by its basis expansion. Yeah, that's what brings in this second sum, and that's what makes the change of the coordinates necessary here. Yeah, that's this kind of tedious derivation that I mentioned before. We do it here, and we do it also for the boundary operator. The next thing we do is, this F is the right-hand side. We are also replacing the right-hand side by its basis expansion. Yeah? And the same we do for the Dirichlet values, or for the right-hand side on the boundary. Let's go one step further, because you might ask, where is the geometry? Well, the geometry is the push forward from the parametric domain into the physical domain. Yeah, it's again represented by the same basis functions and control points. It is somewhere hidden here in these differential operators. Yeah, if we go from Lx to Lxi, then come gradients and Hessians and determinants, etc., of the Jacobian, and they all involve the geometry. So now we have everything in place. We have the solution here in place. We have the right-hand side. We have the boundary conditions, and we have the geometry in place. And let me mark that. These will be the inputs and outputs of our network. More precisely, this right-hand side boundary condition geometry will be the inputs, whereas that one here, the UJs, are the outputs of our network. And now, as I already said, this looks already like a loss function. Let's call it loss function, and let's split it up into the PDE loss. Yeah, that's what happens in the interior of the domain. And the boundary loss, that's what happens at the boundary of the domain. And then this is the IGA net architecture that we have. Yeah, as said, these are the inputs to the network. Then we have a couple of fully connected feed-forward layers. Output are the solution coefficients, U1 up to UN. The loss function are the ones that we have here. And then we are training this network until the loss is small enough. And let me just compare this to things that are out, for example, physics-informed neural networks, the PINs or the deep O-nets. So if you ask, how is this related to PINs and deep O-nets? Well, to PINs, I don't know, but to deep O-nets, I would say you can interpret it as a deep O-net, but instead of having the one network where you learn the basis in deep O-nets, we give the basis in terms of B-splines or NURBS. So it's a kind of comparable to deep O-nets. And let me make the point. It's not competing with deep O-nets. It has a different, it's a vision. We are not trying to be better than collocation IGA, or we're not trying to find an optimal basis for this particular problem. And I think that is what deep O-nets really do. No, we say we are lucky if we are as good as classical collocation IGA. So we are not trying to use a network to become better. And the other thing that kind of links to PIN, for example, one thing we don't have as an input is the point in which we want the solution. Yeah, so in classic PINs, and I think also in deep O-nets, you have as an input where you want the solution, yeah, and kind of the collocation points. And this is something that we don't have as inputs. We say we agree on, we use, for example, the reveal points as collocation points, and they are hard-coded then in the loss function. Another question is, do we need to separate the training from the evaluation, from the inference? In practice, we do it, but strictly speaking, we don't need it. So we can use this whole thing as a different way to solve the least squares collocation IGA system. Yeah, so we can train the network on the fly, but practically we do pre-train and then evaluate afterwards. Let me give you some.
Professor Möller, I had a question on that previous slide, if you don't mind.
Sure.
So when you say that you're using geometry as an input and you have n number of points, what is like the dimensionality of that input like for the network? Is it the total number of points as a like dimension? Or?
Yeah. So say if you have let's say a 20 times 20 in 2D control points, 20 times 20, you would have exactly this for the geometry in X and Y, so times 2, the same number for this. Yeah, so you have a couple of 100 inputs. So our networks are relatively not relatively deep, but relatively wide. Perfect. May I go to the next slide and then?
Sure.
Okay. So for example, here, what we have here is bicubic, 2D, 7 by 7. And what does that mean? We have, we have 7 times 7 X values, 7 times 7 Y values. Okay, the load vector we encoded differently. So if we just encode the geometry, we have 7 times 7 times 2 inputs.
So that's basically close to like 98 or 100 dimensional input. So if you scale this for like a bigger problem, would that be like something like just too big for the network to learn? So say I go to like a much complicated like shape, which has like, you need like say 1,000 points.
Of course, at some point it becomes untrainable or difficult to train. And there this idea of multi-patch comes in. So we are at the moment training, let's say a few hundred inputs, and then say if we really would need thousands, then better use multiple patches and combine them. Yeah, but you spotted one, let's say, one crucial aspect. If the problem becomes too big in terms of degrees of freedom, unknowns, then it becomes at some point impractical to train the network.
Okay, thank you.
Okay. Okay, so let me get back to this. This was just a toy problem. So we have this quad or this variable analysis. As said already, 7 times 7 bicubic B-splines. We train it for, let's say, all these 1, 2, 3, 4 configurations of the geometry. We train it for 12 different right-hand sides. We train it for 12 different Dirichlet values that we prescribe here. Yeah, so it's all Dirichlet. Here it's always 0, and then it linearly along the boundaries goes to the value that we prescribe here. You see here we use some 50 neurons and 7 layers, ReLU activation function, all very, very standard things or settings. And then we stop the training if for 3,000 epochs we don't see a huge any improvement in the loss value. And this is now just eyeball norm. Yeah, so this is a scenario that has been seen during training. Yeah, so the geometry is known, these boundary conditions have been seen, this load vector has been seen, and it qualitatively, and let me repeat this, we are not trying to come close to, let's say, an honest or accurate IGA simulation. Yeah, it's just about the qualitative results. Yeah, we get this. And then, yeah, we have an unseen right-hand side here. Yeah, qualitatively, it also fits to or meets 1.4. We have now an unseen right-hand side, an unseen geometry, an unseen boundary value, and it all qualitatively works. Yeah, so it in some sense validates that this approach of IGA nets does work. This is all for Poisson, I should say. And what we then tried is hyperparameter tuning. This addresses a little bit what you asked. Yeah, so here on the x-axis, we have the number of coefficients per direction. Yeah, so this would be 64 squared, 124 squared. We did it in 2D, yeah. And then we try to understand, is it the number of layers? Is it the number of neurons? What has the biggest influence? And what we see here, if we use one layer, one neuron, yeah, so that basically means from a 16 squared input down to a single neuron and then output, yeah, it's a very extreme compression. We are able to, after a lot of training, we are able to get an L2 error below 10 to the minus 4. Yeah, and then at some point it stagnates. And for example, this here, yeah, this is below 10 to the minus 6, so much more than we would need for a qualitative result. Yeah, it's still one layer, but many neurons. So 1,000 is maybe 800 or 750 would also work. Yeah, so we just did it, yeah, kind of in steps of 100. A single layer and then many neurons. Yeah, so that supports what I said before. It's not so much the depth that we need, but we need quite a lot of neurons per layer to get, let's say, good or small errors. Let me, because I think that might also be interesting for those who to try to implement something similar. So let's look a little bit at the costs. Yeah, as I said already, we yeah, kind of have to do all these calculations. So I-Laplace, for example, would mean we are doing the calculation with the geometry involved. Yeah, so our code is let's say written in a form that we just write expressions like this, and then would say, yeah, use this as the loss function, and a similar thing for the boundary loss. And the thing I want to point out here is we don't have to differentiate the network if we want physical or derivatives with respect to the physical coordinates. Yeah, that's different than in other maybe pins, for example. Yeah, because, well, we do exactly what we do in finite elements. We work out this, and then the derivatives are on the basis functions, and they can be computed beforehand. Yeah, so the only moment where we need, let's say, algorithmic differentiation or backpropagation is when we want to get the derivative of the loss functions, which with respect to the weights. Yeah, but not to get into the differential operators. And yeah, so the message is we need a way to calculate the B-splines or evaluate the B-splines and the derivatives very efficiently. And you might use the Cox de Boer formula, but that's maybe not the quickest thing you can do. So what we developed based on an algorithm from Lieke and Morgan is this algorithm. So you might recognize a little bit the Cox de Boer form. Yeah, so here are this is the division. This is the combination of two lower order or lower degree B-splines. Yeah, this is if we want values. This is or function values of the B-splines. This is for the remaining derivatives. And what this algorithm, if it finished, gives us is all the B-splines, the function values or derivative values of the B-splines in that particular sampling point that are not zero in this point. Yeah? So we are not getting all the B-splines, but only those that are not zero in this sampling point. Yeah? And then if we want to compute, let's say, the first derivative of u in this point, it's just taking these vector and then dot multiplied with the solution coefficients. How much time do I actually have, Nas? We started a little bit later.
Yeah, you have time. You can continue.
Okay, great, thanks. So this was in 1D, and we tested it. Yeah, so we tested it on a CPU, or actually on an ARM and an AMD CPU, and also on a graphics card. And what we see is, let's say, the more sampling points we evaluate at the same time, because this is all fully vectorized, of course. Yeah, so for example, if you go to 1 million sampling points at the same time, different sampling points at the same time, we really get very, very small compute times per degree, per sampling point, yeah, at least on the graphics cards. So how do we extend that to 2D and 3D, so to multivariate B-splines? The first idea one could have is, because it's a tensor product, we just calculate with the algorithm from the previous slide these three vectors in psi, eta, and zeta direction, then compute the tensor product of this. Yeah, so let me remind you, these B are only flat vectors. The tensor product of that is a very long but still flat vector. And then we dot multiply it with the corresponding coefficients of our solution. But there are two things which are not so nice why we don't do it in exactly this way. The first is, while here we have, let's say, d plus 1 for the first one, yeah, kind of the length of this added up and then multiplied by the number of control points that we want to work on simultaneously as a memory requirement. If we work out this tensor product, the plus here becomes a multiply. Yeah, so the memory requirement grows very fast. Yeah, so it's not for a single sampling point, doesn't make a difference. But if we have, as before, 1 million sampling points that we want to work on simultaneously, yeah, this is quite a huge memory requirement. And the second observation is this C, it's not contiguously in memory. Yeah, so it's stored as a tensor, yeah, in one or x, y, z direction. Yeah, it's you have a lot of memory jumps here, yeah, that you do want to avoid. Let me show you a different representation of this, namely, flattened out, or a very concrete setup here, a very small one just for the illustration. And you see there are these small jumps when we are, let's say, jumping from the x to the next y direction, and these are the jumps in z. They are somewhat bigger in the index. Yeah, so this C would be the one with which we have to multiply, but actually this is all but contiguous. So what we thought about, well, how is the Kronecker product defined? It's defined like this, and it has a very nice property. It has the property that the product of two Kronecker products, the classical matrix product of two Kronecker products, can be written as the Kronecker product of two matrix products. Of course, only if AC and BD, let's say, are well defined. Yeah, the matrices need to have the right dimensions. And if this is the case, then we can write one matrix of interest and an identity Kronecker product with an identity matrix, matrix multiplied by an identity matrix, and in the Kronecker product and another matrix, like this. Yeah, so actually this here, what we have is what we would like to compute. Yeah, let me go back. So these are the things that we would like to compute. Yeah, and we can replace this by several matrix products. Yeah, so again, I'm writing it here. So these are the three, or the Kronecker product between three matrices that we want to compute. We can split it up with this decomposition from the previous slides like this. And when we have that, we can apply a very nice algorithm that has been introduced by Fackler in 2019, where it kind of goes in rounds. Yeah, so it peels off one dimension and then goes over this round, and then over this round, and then over this round. So I just give you the pseudocode here. What it does, it takes this, the relevant coefficients from this big tensor, does a reshape on that, but this reshape is no movement in memory. It's just you look at the same piece of memory, with the different meta information, and then you kind of peel off the first dimension multiplied by the first univariate B-splines, the second and the third. Yeah, so this is a very efficient and especially memory efficient way to calculate, let's say, the multivariate B-splines. And how efficient it is, we see here, same plot, two different CPUs, one GPU, and we see that especially on the GPU, we can really go to large number of sampling points we do simultaneously, and get quite some performance. Let me skip this slide and come to one of the last ones. So what we try to do, remember we want to do this design through analysis workflow, and next to the IGA nets, we are also working on some real workflow where with multiple devices we can work on the same model. And by model, it can be an IGA model. It can also be an IGA net model, sorry for that. It can also be a classical IGA model. For that, we have an open source software called Gizmo, Geometry plus Simulation modules. And let me show you one little live demo, then you get an idea of what I mean by this. And I hope that this, let me stop sharing for a second, move to this and share again. Yeah, so this is the, you see this screen, Ness?
Yes, we see. Yes,
Yeah.
yes.
Okay, so this is the system. It's a prototype, I should say, that we are working on. Yeah, so let's assume we do a simple 2D Poisson thing. Yeah, we are adding it here. Yeah, it's already configured that it is zero Dirichlet conditions, a load of 1 here, and okay, let me say, well, I want to refine it because there are too few degrees of freedoms, and maybe I want to change at the north side of the domain. I want to change the boundary conditions, let's say to this, for example. So has changed. What I now try to do is connect with the second session to this, and then you see what I mean. Yeah, do you also see this moving picture?
Yes.
Yeah.
Yes.
The second session is now as said in the abstract, a VR device. Yeah, and well, all these things like setting up the boundary conditions, that's of course something one can easily do on a flat screen. But maybe if someone is more interested in the in the geometric modeling, then this person wants to connect via a VR device. Yeah, okay, sorry for the technical issue. So now you see, hopefully, what I see from the VR device on the right part of the screen and what the other person with the flat screen would see. Yeah, and now what I can do is I can change the geometry. Yeah, you see it's changing everywhere. That's maybe something that makes more sense in the VR device than on a flat screen. Yeah, and also, if you would now add a, yeah, that was just a flat thing. If you would add a volumetric thing, just a volumetric object, let's also refine it. Yeah, so you see it also appeared in my virtual environment or in my virtual scene. And now if you start moving this and wonder how it looks inside, yeah, then you look inside and here you see this grid. So all these points, this, for example, is one of these control points in the interior that I spoke about. So I think I am well, getting over time. So let me stop sharing and come to the conclusion.
Very interesting.
Yeah. Okay. So what I try to show you today is the combination or the seamless blending between classical IGA simulation and scientific machine learning by this collocation IGA based IGA nets. Also, and again, I apologize for the technical hiccups for a moment. A concept idea of how we want to integrate this into a design through analysis workflow. And there are a couple of things that we are currently working on. But yeah, let's stop it here. Thanks very much for your interest.
Yes, thank you. Thank you so much for your great talk. Now we open the floor for more questions if there is any more questions. Okay, do we have any questions for the speaker from the audience?
Hi, Professor Möller. This is Raj.
Hi, Raj.
Yeah, I just have a question on just very naive question. Why the IGA Galerkin gives better error than the IGA collocation, like you showed in the first few slides, right?
Yeah. So IGA Galerkin IGA has a very well-developed conversion theory. It converges much better, and depending on geometry, etc., it converges optimally. And it's known that collocation does not converge that optimally. And on top of that, it in the multi-patch case, it has even some other problems conversions problems. But yeah, that's in some sense the price that we pay. We could also we tried Galerkin IGA or that's something like a deep Ritz method that does actually work, but then the assembly is much more expensive. Yeah, so let's say it's as expensive as in classical Galerkin IGA.
Okay. So for this, the basis function is a spline, right? For here, which we chose. So like in the IGA Galerkin, if you change the basis function, will that also affect the convergence or not?
Sorry, could you repeat that?
So if in the IGA Galerkin projection method, so you also use the spline basis function, right?
Mm-hmm.
So if changing the basis function to the like Jacobi or Legendre, will that help for the convergence of in terms of the speed for the IGA Galerkin?
I don't think so, because unless you change the basis function to, let's say, a lower order polynomial, then yes. But what makes maybe I can go So what causes these high costs is that you need a relatively high Gauss or numerical quadrature rule.
Okay.
If you want to integrate these, not at low order. Yeah. So if you just have a first order B-spline, that is the simple fem head function. But if you go to higher order, you need quite high quadrature rules. To be honest, there are ways to speed up the assembly of IGA matrices. That's a big topic in IGA, I should say. But if you do it the, let's say, most naive way, then you see, quite high compute times for the assembly.
Okay, that makes sense. Yeah, thank you very much. A really wonderful talk. I enjoyed it. So thanks.
Thank you for the question.
Yeah, thanks.
Do we have any other questions for the speaker?
I had a small question. This is like, again, Varun from Brown. So Professor, have you like thought about how you could reuse this model in case I have like minor modifications in the geometry? Like, so say I have like a hole in this plate on this slide. Can I reuse this model, or do you have to like train the model from scratch?
No. It's really good that you asked that, because let's say this network, when I say all, please see it in quotes. Yeah. So for all the geometries that I showed to it during training, and similar ones, it can be used. Yeah. So what we, for example, do, this was just we show it 1, 2, 3, 4, 5, 1, 2, 3, 4 different geometries, and then within these geometries it can kind of work. Yeah. If we show it a geometry that has the boundary here, that does work. That's very much like in pins. It is good in interpolating, not so much in extrapolating. Yeah. So if we would show it only these 4 geometries, then expect that it can, let's say, work for a completely different one. So a snake geometry, that of course doesn't work. So the idea that we have is we train it for the typical set of geometries that for this particular application are of interest. And that very much depends. It could be, for example, wings. Yeah, if we talk about aircraft wings, they have a very similar shape. And if we show it, or if we train it for a lot of different geometries of this wing type shape, then it should be good at predicting also for an unseen wing type. And the thing what I said in the very beginning, and if not, we see that the loss function is relatively high. That means the error is relatively high. So we could make a threshold and say, if the loss for example, an unseen geometry is high, that tells us that the network does a poor prediction. So then we kind of on the fly retrain for that geometry. And that's the nice thing of the in paradigm. It's not like we have to first train and then can only use it. If we use it and then figure out that the error is high, we on the fly retrain the network.
Okay. For the new geometry, you won't know the error, right? Because you don't know the solution.
No, you don't know the error. Well, you could use similar techniques like in finite elements or IGA, error estimation, that you have the constant definer. But you're right, So, but let's keep it at, if the loss function is larger than you would expect. For example, let's say if we expect something that we think our loss should be somewhere between 10 to the minus 4, let's say. And if for one geometry it is very, very high, we could say, well, probably this geometry, the network doesn't understand this geometry. We have to do something.
Okay. Yeah.
It's a kind of error indicator, not estimator.
Yep. Okay. Thank you.
Do we have any other questions? Since our second speaker is here, so I think it's time to move on to our second talk. Thank you so much for your great talk. And now you can stop sharing and we will continue with our second speaker. Dr. Qureshi, can you hear me?
Yes, can you hear me?
Yes. Can you try to share your screen to see?
Hey, just give me. Yeah. Can you see my screen?
Yes, and can you put it on presentation mode?
Yeah.
Please. Yes, thank you so much. So our second speaker is Dr. Ahmed Qureshi. He will be giving a talk on neural PDEs for robot motion planning. Ahmed Qureshi is an assistant professor of computer science at Purdue University and directs the Cognitive Robot Autonomy and Learning Lab. He is an associate editor for IEEE Transaction on Robotics and IEEE Robotics and Automation Letters. His research focuses on robot planning and control, aiming to deploy robots in dynamic human environments. His work spans motion planning, robot manipulating, and mobile navigation. Dr. Qureshi has received multiple awards, including the 2024 Outstanding Associate Editor Award from IEEE. He holds degrees from NUST Pakistan, Osaka University, and UC San Diego. With that short introduction, the floor is yours and you can start your presentation.
All right, thanks for your introduction. So let's get started. The topic is like neural PDEs for robot motion planning, and I'm assistant professor in Purdue University in the Department of Computer Science, where I direct this cognitive robot autonomy and learning lab. So today focus is on robot motion planning, and motion planning is a way for an agent to coordinate its like joints to move from one point to another without collision while satisfying some additional constraints which could be task related. And these problems has applications like in any time robot need to move, you need a motion planner. For example, if you have a like a 3D robot or some 3D object and you want to make it move from one point to another while avoiding collision, you need to solve the motion planning problem. Similarly, in autonomous driving, making those car moves respecting the curvature constraints, you have to solve the motion planning problem. Then in robot manipulation, as well as like beyond robotics, motion planning tools are needed, let's say, in computational biology for finding protein folding paths. Similarly, in computer graphics, like generating the motion of those animated characters, you need to solve the motion planning problem. Mathematically, this problem looks like this. So the motion planning problem translates into a trajectory finding problem, and where you are given some start and goal. So there are boundary conditions on the initial state and the goal state. And this trajectory needs to satisfy some objective function J, which could be like path length, and which could include like collision avoidance constraint. And then we also add some weightage that where it should terminate once the trajectory reaches this goal state. So this simple equation that is highlighted in red, this is called like geometric motion planning problem. And it appears whenever a robot moves and they just only have to adhere to, for example, collision avoidance constraint. As you can see in this robot, it is coming out of this tight scenario confined by tables, and it need to come over top, grab this blue object and move it to the yellow target marked as a Lego block. Now, on this trajectory, we can add additional constraints. For example, we can add symbolic constraints saying that before you reach your final destination, achieve some sub-goals. For example, some sub-goal A and some sub-goal B before you reach your destination. And how it translates to our real world. For example, you have this confined environment and your robot needs to retrieve some object. In this case, this robot needs to retrieve this yellow object, which is a banana, and then it needs to move. As you can see, it cannot reach there. It needs to move this blue red object and then the blue object out of the way so that it can clear its way to reach the target without collision. And the application of these tasks is like, for example, you have a home robot and you want them to fetch something from your kitchen cabinet or refrigerator. They will have to rearrange and solve these kind of problems to retrieve and fetch objects for you. And then on top of these constraints, we can also add kinematic constraint. They are function of robot joint configuration. Basically, they limit the joint space. And they usually appear when your robot is physically interacting with the environment. For example, if you imagine a robot opening a door, now robot hand is attached to the door and door hinge is controlling the robot motion. And these constraints induce a like thin manifold inside robot configuration space where the algorithm need to find a solution. For example, if the application I mentioned here, like robot is attached to the door and now it needs to respect its physics in order to generate the door opening motion. And other, like, for example, you will see this robot will pick up this glass and move it from one point to another. And the constraint is like it cannot tilt it along certain axis to prevent liquid inside it from spilling. And then there are like additional dynamical constraints. They are function of time, and they basically control the robot speed and the impact force that it applies in the environment that it is interacting with. For example, in autonomous driving, it could be like high speed navigation or low speed navigation, depending on the scenario. So robot need to plan how fast it can interact with the environment, and that indirectly controls the force it applies on the environment. So today's talk will focus on first the geometric planning, and then we will also discuss a little bit about like kinematic constraints. So that will be the focus of today's presentation. And when we add these constraints introduce some forbidden space inside robot configuration space and some feasible space. And then the objective of these algorithms is to find the solution in these feasible space. Okay, so let's get started. This problem of geometric motion planning, it was introduced in 1983 by 3 sets of papers where they asked a simple problem of how to move a piano from one point to another without collision. That was a very simple problem. It is solved now. And but since then, like many algorithms have been proposed to solve this problem. And as I said, it has application beyond this piano mover problem in controlling the robot motion in computational biology as well as in computer graphics. So since then, many algorithms have been proposed, and this is a brief taxonomy of those approaches. There are control-based approaches that require build some control theoretic approaches, such as model predictive controller, but they plan robot motion locally. They usually do not find a global solution. Then there are like heuristic-based methods that discretize the space. For example, A star and D star, however, they suffer from the curse of dimensionality due to discretization. As your robot configuration space increases, the discretization become intractable to handle. Then there are optimization-based approaches that introduce some nice numerical optimization algorithm to solve the motion planning problem. They suffer from local minima, and often they are unable to provide some global solution to the trajectories. Arguably, the most used algorithms are like sampling-based planners. I will discuss them briefly, and they find global solution. They provide some theoretical completeness guarantees that if there exists a path solution, this algorithm will eventually find that path solution. So let's discuss briefly the sampling-based planner. They construct a graph. They randomly sample the feasible space, which is collision-free space, and they find the nearest neighbor and connect this node to the tree. Okay, and they keep repeating this process until eventually a sample will fall in the goal and it will be connectable to the tree. Then one branch of the tree is the path solution. As you can imagine, like these methods, they need to generate a lot of samples, and so they are not computationally efficient. So, and especially when we increase the robot dimension, they take a lot of time to find the path solution, which is not ideal, especially when we are deploying robots in our daily life environment. We want methods that are real time and efficient and are easy to obtain. So then, like, new class of methods came, which we call imitation learning based method, for example, MPNet. They learn from some classical planners, and then once they are trained, they find paths much faster than the classical planner. For example, in certain problems, these classical planner can take minutes, whereas these learning-based planner are demonstrated to take like just a couple of seconds. So one of the method within these imitation learning-based methods is motion planning network. So let's briefly discuss what these motion planning networks do. So we propose through these this set of paper a general recipe that you need for these methods to be able to solve the motion planning problem under hard constraints such as collision avoidance. So our recipe was that you need an encoder network that takes the environment observation and embeds it into some local embedding, or if it is a global point cloud, then it will be latent embedding of that point cloud. It could be a feed-forward neural network, it could be a point net, 3D CNN, whatever you prefer and is suitable for your input observation. The second is a planning network. There is a condition on this planning network that it needs to be stochastic. So meaning that it should capture some sampling distribution for a given goal, and the current state of the robot, it should generate the next state and the distribution, feasible distribution around it. So these were the key recipes, and then you need data from some classical planner to train them in a supervised learning way so that these models can be trained end to end. Then we plugged these two modules into a recursive planning algorithm that finds end-to-end path and provided some worst-case theoretical guarantees. So once, let's say, these neural networks are trained, we use them in a bidirectional manner. So we had a boundary condition that this trajectory needs to start at some start state and then end at some goal state. Then these two neural networks placed opposite to each other, they plan toward each other. And they generate samples. And if you think about it, they are basically decomposing a bigger planning problem into a sequence of smaller planning problems. For some of these sub-problems, there may exist a solution. We assume if there exists a straight line between 2 points and it is not passing through this black obstacle, we have solved that sub-problem. But there may be some sub-problems that would be remain unsolved. For example, these beacon points that are highlighted with orange color, and we use them as a new start and goal for our neural network, and they generate the remaining waypoints to find a path. But there may be cases that where our planner, because it's a learning-based approach, it just approximates some distribution, so there will be some failures. So in those cases, we outsource a sub-problem to classical planner. So now classical planner does not need to solve the entire problem. It is just solving a fraction of it. And this is where from these algorithms get the completeness guarantees. And eventually this method will lead to a feasible path solution. We demonstrated it on a variety of scenarios. Like I said, the planner need to be stochastic. This motion planning network paper, they drive stochasticity from using dropout during execution. And then we demonstrated on various problems, like it can generate informed trees between a start and goal. It can find a path very quickly. So here in this 2D mass, we randomly sample start and goal, and you can see within a blink of eye, it emits out a path solution. Then this is for a SE2 rigid body connecting two given start and goal. And if you replace the data of these planner from, let's say, some constraint planner that adheres to some kinematic constraints, then they can also solve like constraint problems such as generating samples on the constraint manifold. Here you can see on this sphere manifold, once you learn the neural network, we call it CompNetX, it is sampling in the region that potentially contain the path solution, whereas traditional sampling will have to sample this entire space before it can retrieve a path solution. So here's a demonstration. This robot need to throw all these bottle and cans into the trash bin. So here we just have the collision avoidance constraint. And then it needs to reach to to this cabinet door and open it from any random starting configuration to the final fully open goal configuration. Then it need to fetch this black and red mug and move it to the tray without tilting. So there is orientation kinematic constraint on it. And finally, this robot need to like move this picture into the cabinet again without tilting. So this imitation learning based method, the advantage is if you see their planning time, this CompNet X times RRT Connect, their planning times are much lower than classical method because they have to sample the entire space. And we also demonstrated on real like toy bartender setting where the robot will throw these cans and empty bottles into the trash bin. And once that's done, it will move this pitcher and cup like without tilting to the tray. Okay, so now we have planners like we have like sampling based planner, which I said like can take minutes. We have learning based planner, which use data from those classical planner and they can find path in second. So although they improve the computation time, but if you think about their data generation time, it can take a few hours or it can take up to days depending on your problem. So are they really bringing the advantage? Like, okay, some people say now we are all dealing with large scale data, so why not just gather data for this learning based planner? But I think the ideal planner would be something that finds paths in few minutes, that finds path even faster than seconds, and then the data generation time is just few minutes. So can we have those planners? The answer is yes. If you design these methods to be physics informed, they can relieve you from gathering this expensive data set and they can directly learn to solve that PDE equation. And once they are trained, we show that they find paths even faster than those learning-based planners. So the remainder of focus of this talk will be on this PDE-based robot motion planning algorithms. So we introduce a new taxonomy here called like physics-informed neural motion planner, and I will discuss the algorithms that we proposed here. So I can take a few questions here if there is any question. Okay. So.
Do we have any questions? I don't think so.
So
You
let's
can continue.
go into this physics-informed neural motion planner. And the question is, which physics equation can be used for robot motion planning between a given start and goal? And the answer is like we use econal PDE, and this econal equation relates arrival time between some given start and goal to some speed model. So classical algorithm that solve this equation is fast marching method. They discretize the space and do numerical optimization to find the solution to this econal PDE. And the solution is this arrival time field. Like if the robot follows this arrival time field, it can navigate from one point to another. And the speed field here basically describes what are the feasible space and not non-feasible space. The speed in free space will be maximum. However, speed in this obstacle spaces will be 0. And then when you solve this equation, the arrival time generate these kind of wave fronts that can guide the robot from one point to another. However, this FFM method, it cannot be scaled to higher dimension. Usually robot are like 6 dimension if you are thinking of robot arm, but if you are thinking of humanoid robot, their dimensions vary from 18 to 72 degree of freedom. So these FFM based method, they cannot be scaled there. So we need something that does not require discretization and that can be scaled to higher dimension. So we observe few properties of this econal equation. One, when we solve the motion planning problem, we noticed that it should have this symmetric property. So this implies that the arrival time from start to goal and arrival time from goal to start under simple Boolean avoidance constraint should be equal. So there is this symmetric property. Second, when my start and goal are same point, the arrival time should be 0. Third, when one of the point is an obstacle, so let's say there is a y which is an obstacle, then the speed will be 0, then the arrival time should be infinite. Okay, because this is the relation here. If this thing is 0, then this will be a very large number. So if you notice these properties, they are very difficult to for neural network to learn. Like neural network cannot predict solve for these kind of cases where arrival time is like close to infinity, and or whenever your start and goal is an obstacle or far from your desired constraint manifold. So we introduced a reformulation of this econal PDE that satisfy these properties. And then we also introduced some progressive learning strategy to help guide neural network solve this problem. So let's begin with reformulation of this econal PDE. So we factorized the econal equation. We said, okay, let's define this arrival time as ratio of your Euclidean distance between x and y divided by some tau, and neural network will predict this tau, and we can say, okay, whenever start and goal are same, that this tau can be 1, and this arrival time will be 0, because this distance will be 0, this arrival time will be 0. But when one of these is an obstacle, we can make this tau to be predicted as 0, and then this relation will hold this third property. For the symmetric property, we adapted neural architecture that you can check in our paper, this anti-field neural time field for physics-informed robot motion planning. So let's assume this neural network is a black box, it's a simple neural network, but there is some articulated structure, symmetric operator in the architecture design that you can check on the paper. But for simplicity, let's assume this is some neural network. And it takes your start and goal, and it predicts tau. And then we can use this tau to parameterize this factorized econal equation to get the arrival time. Once we have the arrival time, I can plug it in the econal equation and solve it. Okay. So now this new formulation is easier to train because tau is between 0 to 1, which is easier for neural network to predict. Second, we noticed that this econal PDE also lacks unique solution around obstacles. Like whenever there's obstacle, the feature of this wavefront become very sharp, and there are multiple solutions. If you see this animation, there are like these sharp features around near the obstacle, which leads to multiple solutions. And we noticed that neural network cannot correctly solve this equation because the equation is ill-posed. So we added another thing, we added a viscosity term based on Laplacian, which made this equation semi-linear elliptic PDE. So now we have this original, like this term, which is norm of this, the gradient of this arrival time plus this epsilon times Laplacian is equal to the 1 over speed. Okay, so now this equation has a smooth and unique solution. And when I add this factorized econal equation formulation into my equation here in brown and do the differentiation, it gives me this relation. And this relation relates this predicted speed to this predicted tau. So my neural network will take start and goal, it will predict tau, and I will use tau and its gradient to parameterize this equation, and then from this equation I can get the speed field. So just to repeat again, we had this semi-linear elliptic econal PDE. We plugged in this new factorization for arrival time into this equation, did differentiation, and then we got this equation of this complicated equation that you see here. So now I have neural network that take the start and goal, predict tau, and then I can use the gradient to predict the speed. To train this neural network, I compare this predicted speed to some expert speed model that human defines. And the speed for the model simply says any given point, it clips based on the distance to obstacle. Okay, so you can think of it like the speed will be some constant value in free space, then this d will be minimum in obstacle space. So this is the data we need to train this network. some sampled point of robot configuration and their distance to obstacles. And then we can use that distance to define this expert speed model, which is compared against this predicted speed model to train this neural network. So the only data is robot configuration samples and their distance to obstacles. So unlike imitation learning based method, if you recall, they were needing trajectories from classical planner, which were very computationally expensive to obtain, but these samples are much faster to obtain. You just need to randomly sample robot configuration space and compute and call the Boolean checker to compute their distance to obstacle. Now we discussed the reformulation based on like these last two properties, and we also added a viscosity term to make it semi-linear elliptic. Now let's discuss this progressive training strategy. So during training, we noticed that if we start from this this last alpha 1 when speed is 0 around obstacle and or inside obstacle and some constant value in free space, it's very hard for neural network to converge to this space. So what if we gradually lower down the speed around obstacles and train neural network on this, let's say alpha equal to 1/3 setting where configuration can penetrate a little bit into obstacle space, then we keep hardening this constraint over time during training. And we notice that it really helped converge neural network to a better local minimum. So our expert speed model that we defined based on distance from the obstacle now has this alpha parameter, which basically scales it up or down. So if this alpha is high, then we are saying that it should have a very low speed in obstacle space. So as this animation shows, we gradually reduce the speed during training. So maybe for first 100 epoch, it will have some alpha equal to 1/3. Then as the training epoch progresses, this alpha will be increased. So now we have all the ingredients, and we have this neural network that takes start and goal, predicts tau, and then I can use its gradient to predict my speed field around goal configuration, as well as I can take gradient of this with respect to x and compute the speed field around my start configuration using this equation. And now I have these two predicted speed. I define my ground truth speed, and they are, you see little alpha here, so they are like based on progressive learning strategy that I mentioned a moment ago. And then we train this network through some loss function between this predicted speed and ground truth speed. Let me grab my cell phone to keep track of time. Okay. Now, once this neural network is trained, I can use this neural network to infer the path solution. So given any start and goal, this neural network will predict the tau, and then I will use this tau to parameterize this new factorization that we introduced to predict the actual arrival time field. Then we will also use the gradients to predict this speed around start state and the goal state, and then we can take gradient steps toward the arrival time field direction to update my start and goal, so they will iteratively move toward each other, leading to a path solution. Okay. So these are the results. So this is in home environment, and the robot had to go from one point to another. I don't remember the color coding, but these are the methods, and for each method we demonstrate this path. And you can see like the physics informed method, which is ours with viscosity term, it has lowest planning time. The path lengths indicate that those paths were smooth, and they had some safety margin from the obstacle, so they were not taking any sharp turn around obstacles, so they were taking smooth turn, and the success rate was higher than all other methods. Anti-field is also our method, but it does not use viscosity term, and its planning time was a little bit higher, and the success rate was somewhat lower than the method with viscosity term. So this simply indicates that the method without viscosity term had trouble training the neural network because it wasn't correctly converging to some correct local minimum. This FFM is the fast marching method. It uses discretization and numerical optimization to solve the econal equation. And you can see like its planning time are much higher than this neural network, and the success rate is somewhat similar. This IEF 3D method, it's an imitation learning based method. It takes data from FFM. So we had to run FFM for a long time on all the planning problem, gather large scale data to train these neural network, and then its planning time are higher than our method, and success rate is also relatively lower. And then these are sampling based method that I briefly discussed. They create a tree by randomly sampling the space. There are different versions of it. Their planning times are much higher, and some of them have lower success rate because of the time limit we give to it. However, if we let it run as they have completeness guarantees, they will eventually find the path solution. Okay. So these are the two papers for the Overs method. It uses this Laplacian, and then the second paper which has this without viscosity or Laplacian term. So we also demonstrated on this 6DOF robot. It is going from one point to another in these confined environments. We do not have, if you see this comparison table, we do not have FFM here because it cannot be applied to this higher dimension. The discretization gives us error like out of memory and those kind of issues. But other methods like sampling based, they are scalable. However, their success rates are much lower because of the time limit we give it to it. But our methods, you can see they just take like sub-seconds to find the path solution. And this is the data generation times. Like in robotics, generating data is very hard and very time consuming. So you can see like in simple, this 3D environment, in this home-like environment and manipulator, this imitation learning based method, it had to gather data for like 21 hours. And then in Gibson, because we had just 3 environments, so it took like 5 hours. Whereas our method, they take like 1 second, 2 seconds at max, like less than 1 minute, because all you need is like samples and their distance to the obstacle. Okay. Now, if I replace my expert speed model, so before we had this obstacle here and we were computing the distance from obstacles. So if I replace this data with my some distance to the kinematic manifold, then I can even train these neural networks to solve the kinematic constraint problem. So all you need now is samples and their distance to some constraint manifold. Constraint manifold is, let's say you have a robot and it is opening the door. So that door motion defines some constraint manifold. If you have a robot and it is carrying some glass filled with fluid, it cannot tilt it freely. So that is introducing some other constraint manifold. And when you have these kind of manifolds, we usually define them like mathematically, and then we are able to compute the distance of any robot configuration to the manifold. And traditional method, they usually use projection sampling to project each sample to the manifold. Here, all we need is random samples and then their distance to the manifold. And the way we define it, that the speed will be high when the sample is on the collision-free manifold, and speed will be low when the sample is in obstacle space or away from the manifold. Then we train this network in a similar way. We gather a lot of samples. These samples go as a pair into this neural network to predict this tau. Then we use this tau to parameterize this predicted speed equation. And then we define the loss function between this predicted speed and the ground truth speed. And we train the model, and it can solve the kinematic constraint manifold problem. So here you will see it is opening the door. That is one constraint. And then it is moving this cup filled with soda from one point to another without tilting. So now if you see the planning times, again, this physics-informed method is much faster than the C by RRT, which is a sampling-based planner, or this CompNetX method, which is imitation learning-based method. This CompNetX had to get data from C by RRT for training. But during execution, their planning time is relatively faster than C by RRT. But you can see significant margin between ours and this imitation and sampling-based method. Success rates are somewhat similar. And but if you see the data generation time, this imitation learning based method took like 12 hours to gather the data, whereas our method in this constraint problem took 10 minutes. And then like the training time of all these models were somewhat similar. So this our paper, which uses this physics informed method, is published here. You can check it online, and these are the references for other papers. Now, getting to the conclusion. So if you see the progress from in the field of robot motion planning, we are aiming for methods that are computationally efficient, that we can deploy on the robot, and the robot should be able to find solutions almost real time. Okay, so this problem, as I said, it was identified in 1983, and since then many algorithms have been proposed. Sampling-based, search-based method, they find paths in minutes, but if your problem become too complicated, they often suffer from the curse of dimensionality. And then there are imitation learning-based method. They are trained on the data gathered by the sampling-based methods or search-based method, but during execution, they find path much faster. However, if you think about it, anywhere where the sampling-based planner will fail, gathering data will become really complicated, and we won't be able to get these imitation learning-based methods. So even though they take hours to days, but there can easily be problems where this become intractable and it will become very hard to gather the data. Then we have now physics-informed method, whose data generation takes few minutes, and planning time takes like sub-seconds. And now our future goal is like how we can further reduce this time from few minutes to even like close to this 0-second time scale, and how we can go further from the sub-second and also add some kinematic or dynamical constraint that I mentioned. Those are a function of time. And then we also are looking into cases like how to scale it to like a more complicated robot systems in a scalable way. So that's the future that we are heading toward. So I try to be fast with this presentation because I have meeting right after this one. So I have to start another meeting at 2. So I will conclude. So and this is my lab, and we have many robots and in our lab, and this is a huge lab combining like undergraduates, master, PhDs, and hopefully now we will be having postdocs as well. So my lab has multiple PhD positions available for spring and for fall, and we also have some postdoc positions available in our lab. So if any of you or you know someone interested, like please refer them here, and they can reach me out through this email. So this marks the end of my talk, and you can visit our lab if you want to see more robot videos. There are many there. So just check them out, and now I will open the floor for question answer.
Thank you so much for your great talk, and thank you for waiting longer today to start your talk. Now we open the floor for questions. Do we have any questions from this audience for the speaker? Yeah, our research group, people don't focus on robotic stuff.
Yeah, I know.
But
So
yeah,
that's totally understandable. Yeah.
Yeah, it's more like control, algorithm, and yeah, physics informed. So I think we don't have any questions. Thank you so much again. And I think it's time to close the session. Thank you
Okay.
everybody for joining us today, and thank you for your great talk, Dr. Qureshi. I hope everybody.
Thank you for having me. Yeah. Okay. Thank you.
Yeah, I hope everybody has a great weekend ahead. Bye.
Thank you.